Hello everyone. We'll wait for a few more minutes for everyone to join in, and we'll be starting in the next 2 minutes. Hello everyone. We'll start the webinar now. We welcome you to our webinar, Overcoming the Real-Time Data Processing Challenges of ETL Tools with Confluent. I would like to introduce you to our presenters for today. From Confluent, we have Todd McGrath. Todd is a lead solution architect with Confluent. Todd not only comes with an extensive software delivery and technical capabilities, but also has hands-on experience in sales, partnership, and business development. He's an effective communicator with a proven history of delivering measurable results. From CIGNEX Datamatics, we have Divya Jain with us. Rajesh is a project manager and practice head at CIGNEX Datamatics. He has over 12 years of experience in building various open source solutions and is currently leading Confluent initiatives at CIGNEX. Divya brings in over 9 years of experience and is a lead consultant at CIGNEX Datamatics. She has built various large-scale and scalable solutions using Java J2EE and Hadoop frameworks with SQL and NoSQL databases. We welcome all the presenters to the webinar. Before we begin, we would like to highlight a few points. The webinar is being recorded, and the recording of the webinar will be shared with you in a couple of days. In case if you have any questions during the webinar, please feel free to drop them in the chat box, which you can see on the right-hand side of your screen. We'll be taking up all the questions at the end of the webinar. With this, we begin and would like to hand over to Todd to cover the ETL journey.
And hello, everyone. I'm really glad to be here with you all today. I thought we would start when we talk about changing ETL or the ETL transformation journey by first setting up the challenge, or what's the problem that we face as architects in the world today. And for that, I have a diagram that shows enterprise architectures that I think will seem very familiar to many of you. One of the things that we are faced with larger enterprises is the idea that there's many components that make up our overall architecture. It might be traditional databases, it might be microservices, third-party software as a service, traditional data warehouses, etc. And a central question to gain value out of these various components is how do we integrate the data from the various sources? Traditionally, this has been handled through ETL jobs or maybe even messaging queues. And these ETL jobs are represented by these arrows throughout these various components. And what happened, if we look at the history of enterprise architectures today, is maybe this is 20 years ago or 30 years ago even, when the emergence of these traditional ETL solutions came on the scene. And what you'll see is that over time, these integrations, these point-to-point integrations, further proliferated throughout the environment. And maybe we even added, as I mentioned before, message queues to attempt to answer more real-time integration needs. And over time, these point-to-point integrations continued to evolve. And then lines of businesses within organizations started to ask for integrations as well. More recently, the cloud came on the scene. And these integrations just continued and continued. And at the end of the day, where we are today in most large organizations is frankly a mess. No one intended I believe, their architectures in organizations to look like this. Architectures like this present us with many challenges when we start to think about developing new applications or even managing existing applications. A few of those challenges include the difficulty to scale. It's tough to implement performant integrations when you have so many existing point-to-point integrations. The idea of single point of failure is rampant in architectures, as was previously shown. The data between integrations as they flow through is non-persistent, which means it's non-replayable. Of course, as we saw in that previous slide that I'm sure many of us can relate to, it's complex, to say the least. When things are complex, it tends to slow the development velocity within organizations because there's so much baggage to have to maintain in order to consider developing new applications. And there's also many organizations that still have legacy systems or mainframe systems that they need to maintain throughout. These tends to lead to a high cost. So if this is the challenges today that we're faced, how can we solve them technically? What are some of our options? Let's consider two of the most popular options from a historical perspective. On one hand, we have the traditional ETL approach, and that's really good at answering what has happened in the world. Subsequently, we had the idea of needing more real time, so traditional messaging queues were introduced, and that was better at answering what is happening in the world right now. And both of these solutions have some pros and cons. If we look at the left-hand side, ETL, we have many positives about that solution. Now, there are some drawbacks as well. As we all know by now, the world is moving towards real time, and ETL, traditional ETL, isn't conducive towards real time. On the right-hand side, there's many positives about traditional messaging queues. Near real time is one of them. There's some cons as well. So when our founders of Confluent, the original authors of Apache, Kafka, were faced with these very challenges, they asked themselves, is there any way to combine the positives of both of these things into a new solution? And the answer was yes. They came up with what I'll describe in further detail here, is the event streaming platform, where our founders attempted to take the positives from both of these traditional solutions and innovate to create something new. If we look at a very high-level diagram of how that changes a large organization, we'll look at like something like this, where now, instead of point-to-point solutions, we have a loosely coupled connections between the various components in our stack. Logs, for example, don't need to know that they're being consumed downstream from an app. Or logs might be making it to Splunk with some filtering that are happening at the Confluent platform. As architects, we're told that our solutions should be designed with flexibility in mind. Point-to-point solutions are brittle. Loosely coupled components allow us that flexibility. The Confluent platform, which consists of a few components to make these integrations powerful yet flexible, is what we'll talk about today. This enables all kinds of real-time applications as shown up here at the top. Let's move on to some of the use cases where you might consider the Confluent platform as you move from batch-oriented ETL towards near real-time streaming ETL. Here's a few of the high-level solutions to consider real-time ETL. There are primarily four pillars. Left to right, we've got the idea of scalable and flexible application integration. Moving to the right, we've got the idea of modernizing our batch-oriented ETL jobs. This is especially applicable when we start to introduce more modern, maybe even cloud-focused data warehouses. This allows us to react to events in real time and perform real-time analytics. Real-time is a theme throughout as we move to our third pillar, such as real-time monitoring and SIM modernization, as well as IoT and log streaming. Finally, the idea of multi-cloud and hybrid cloud for use cases such as disaster recovery, and even allowing lines of businesses to develop their solutions across different cloud providers requires multi-site streaming. So these are just a few of the solutions where an event streaming platform, and in particular streaming ETL, can be beneficial towards your designs. Let's take a look at a little bit more detail of streaming ETL. I'm making the assumption that we all know what it is, but I don't want to assume that. Let's quickly go over what ETL stands for. In order to implement streaming ETL, we must be able to extract it from transactional databases in real time, must be able to transform this data, and there afterwards we'll load it into data warehouses or lakes for analysis. Some of the pain points around this is that it's high latency. So as I mentioned, it's brittle, complex, and it's difficult to scale as well as develop new around it. Of course, the business value that we're attempting to achieve is that we're all being asked for more real-time reactions to events. We're also being asked for lower licensing costs and the ability to streamline processes, as well as be flexible with the introduction or even removal of components within our stack. From a high level, an architecture might look like this when we talk about a real-time processing architecture. On the left-hand side, we have various sources. It might be mainframes. We might have traditional relational databases that have connections for things like JDBC and CDC. CDC being change data capture, and something we'll talk about later on. Once the data has arrived into the Confluent platform through the Kafka Connect framework, we're able to do a couple of different things. The Kafka Connect framework is also able to output this data to enterprise data warehouses, as well as maybe Hadoop data stores based on HDFS. We're able to process these events in near real time as well through the Kafka streams and KSQL components of Apache Kafka and the Confluent platform. Let's look at a few more use case examples. I mentioned CDC before. What does that look like? Let's assume we've got a database like MySQL. Using Kafka Connect and the Debezium connector for MySQL, we're able to connect into the MySQL bin log and react to mutation events as they happen in real time. By mutation events, I mean things like inserts, updates, deletes into the MySQL database that are streamed via Kafka Connect into Kafka. Now, the alternative way was having audit columns such as created at or last updated at with a timestamp that our traditional ETL tools could read from in order to determine the mutation events. But with change data capture, we don't need that anymore. We can actually simplify and speed things up by tapping into the basis of most relational databases systems today, and that is a log. In MySQL case, it's the bin log. From there, we're diving deeper down into the previous slide. We can use KSQL to process these events in real time and stream the data out, again, via Kafka Connect out to maybe something like Elastic. Another example could be retail, where we have a stream of purchases from stores or online. At the same time, we have a stream of shipments that have arrived. Combining these two streams of data, we're able to perform some analysis of them in real time and maybe even have a real-time inventory system. Further examples include IoT, We'll see a large use case of Confluence here in a second, but imagine telemetry data from cars. This is what modern cars are doing. And imagine that at the same time, we've got streams of data about the particular car owners from a customer relationship database, for example. Again, we can perform joins on real-time data that's arriving from the cars, combining that with more static data from a customer relationship database, and we're able to create entirely new applications. For example, Audi, one of our customers, is using us to do real-time data analysis from their new cars. We've got a variety of different sensors in these cars that are able to be processed in real time over MQTT, land in the Confluent platform, and perform all kinds of analysis from traffic alerts, anomaly detection, and so on. Confluent founders are the original creators of Apache Kafka. We've written over 80% of Apache Kafka today, and we have over 300,000 hours of experience supporting Kafka. While some of this architecture might seem new to you, I can tell you from some of the logos here on the slide, it is becoming more mainstream than you might think. In particular, we've got use cases from our partners like CIGNEX, and I'd like to turn it over to Divya now to describe that in more detail.
Hi everyone, this is Divya Jain. Today I wish to share with you a very interesting use case based on the details that Todd has described in the previous slides, where we see how an ETL pipeline, a traditional ETL pipeline, can be replaced by Confluent Kafka and how it provides us those benefits. So let's first understand what the real use case was and why do we need it. So imagine there is a system built 20, 25 years old, a traditional SQL-based database, which is being used by so many applications, like 10, 12 applications, consolidating, putting data there into the same database, absorbing data from that database, and continuously growing and growing. Now, since this is the traditional old SQL-based system, it has no distributed capabilities to grow. And there comes a point where it cannot go further. And hence, the impact is something which the applications have to bear. So the applications start going slower and slower, and hence we need something else. So the solution oriented and started to move some part of these applications from this old traditional databases to building a new data warehouse with its own capabilities and having only the responsibility to cater to a certain set of applications. Now, if you can picturize the whole scenario, basically we have on one hand the whole database, which is the older system and being used by a lot of applications, and then on the other hand we have another data warehouse which is subjected to a very, very specific need. This warehouse needs to be synced up with my larger database. It needs to be consistent, it needs to have all that data, and it also needs to be having that data without any latencies. When you imagine this whole scenario, the first thing that comes to mind is an ETL engine. So you would want to build an ETL pipeline to be able to move data from one system to another, in the process doing all the transformations you need so that your application has the data in the format that it needs, and it does not want to rely on the generic data format or the normalizations that it had. So look at the architecture of this whole application. It's on the left-hand side, it says now what the application looks like. When I talk about the whole ETL pipeline being built to interact between these two databases, the problem that the system faces is the business needs actually. It needs to be consistent, but the ETL pipelines, the traditional ETL pipelines, can only work in batch mode. So I can get the consistency, but that's going to be eventual consistency. Then let's talk about latency. I can get the latency by the traditional batch-oriented ETL system, but it's going to be high. I'm not going to achieve low latent real-time or near real-time data syncing. So that's where Kafka comes into the picture, and it replaces the batch-oriented ETLs with its own powers. Design the system in such a way that there were lots of Kafka and producers sitting and getting data from the CDC pipeline, which Todd just described. We pull that data from those databases or data stores and then compile that data and do all the processing that we need, and then move that data to the final target system, which in our use case are basically not one system, but multiple systems. Because this is our source data. This is the data that's coming from my own base central or data repository, and hence not one, but multiple applications would want to use it. But since this is Kafka and it gives you that capability of the same data being used at multiple places by multiple applications in the way they want, applying their own kinds of ETL transformations the way they want to achieve, it gives us that capability. And same data can be utilized by a lot of applications. And we achieved the scaling and the performance issues that we were facing, we could actually push them back, and we achieved what we really wanted. On the right-hand side, we see all the details of the basic high-level steps of the transformations that were needed while this second data store or the data warehouse needs to be built. So as you can imagine, from any traditional ETL pipeline, you would need to do data filtering, you would need to do a lot of validation, and the most important part, you would need to do enrichments and normalization. When you would want to do both of these activities, normalization or denormalization, as you can see, by default would need data from a lot of other entities and a lot of other items also. So it needed the interactions between the data which you are continuously getting, as well as the data that you are persisting. And hence, different topics need to be continuously interacting together. This is a challenge which essentially K-streams and K-SQLs allow us to solve. So high level, if we see what are the implementation features, what did we implement? We had, on one hand, as I said, a database, an online transaction system, which was in continuous syncing with the corresponding data mart, the new data warehouse that we developed. Now, when you're doing that, as I mentioned, latency is our main thing. We need the data to be consistent very, very fast. So we had to tune up the parameters and a lot of configurations, which essentially helped us to achieve what we wanted. So if we see the old systems, initially when the whole thing was happening in SSIS jobs as ETL packages, there we could only achieve the latency and we could only achieve the whole syncing activity to happen once a day or maximum twice a day. But now here, with the capabilities that Confluent provided us, we could pull the data every 0.5 seconds and then transform all that data, and in those transformations, apply those capabilities of in-memory streamings and combining those streams together to be able to sync that data back to my system like every 20 seconds. This is the power that in-memory processing and moving data across the streams, connecting them together, provides us. Next slide, please. Now, since it is a big system, as you can imagine, it was not built in a day, right? So we had to go through phases. We had to go through a series of steps. I would want to just take 1 minute of your time to explain what and how it was achieved, what we did and how we achieved it. Initially, when the first we started implementing, we saw that we are running into the issues of a lot of consumer threads and a high number of CPU utilization, which was pretty obvious because we had more than 100 entities which are being synced up like 24/7. So the number of threads by the number of heartbeats, the session intervals, and all those threads were really, really high. But the only thing that we really ended up doing was fine-tuning 4 basic parameters based on the system needs. That's all. Only 4 parameters that we fine-tuned and we attained and got our whole hardware issues and hardware utilization issues actually in control, and we achieved what we wanted. So it was so straightforward because we could focus all our energy into the actual business logic and what the business logic needs, rather than spending all my time into hardware settings, configurations, and a lot of other things that we normally do in any traditional ETL batch-based ETL system, because they have their own completely different set of requirements and needs. Now, after this, the next piece that went was, since it was we balanced it, we tuned the configurations, there was still a need of further increasing the performance. And when you talk about performance, of course, the first thing that we want to tune is how we actually commit the reads that we have made, and how we can further enhance the whole transformation layer of my ETL pipeline. This is where we did and go for very basic changes, from moving from an auto commit model to a hybrid model of sync and async commit model. And also, we went in and plugged in inside the system the case streams. Using those case streams, if you remember from the architecture diagram that I just showed you, we wanted to be able to use data from a lot of topics, Kafka topics, which were going on in parallel. So if I wanted to use them, the traditional system was essentially going and taking back from the database. Every single step had a database interaction. But Confluent provided us the capabilities of joining these streams together using the Kafka streams, because you can plug these two things together, and as many as you want actually, and allow that thing to happen in memory. This is the whole phase and journey through which we achieved, and we moved from a traditional batch-based system, which took, let's say, 12 hours to have my data finally inside my system, and bringing that time to basically 10 to 15 seconds. To summarize the whole thing, if we talk about from the business needs, what we had and what we achieved, we got consistency, because the whole 100+ entities were being synced up 24/7. We didn't have to wait for them. We didn't have to wait for the batching to complete. And we achieved that consistency by having this whole Kafka sync up, Kafka pipeline syncing data, and with the inbuilt fault tolerant capabilities that the system had. We achieved performance, we achieved low latency, and we achieved the denormalization and transformations that we wanted in the maximum throughput that we could ever dreamt of. So having said all that, I would hand over this to Rajesh to talk further about streaming architectures.
Thanks, Divya. Hello, everyone. So we have gone through a journey of what exactly the Confluent is, right? And Todd has very nicely summarized the capability of the Confluent, in fact, the Kafka, and what it can do to businesses. And Divya has also covered a specific use case, what we have implemented so far using the Kafka and the Confluent as a framework. Now let's try to understand for the businesses, or in fact a different industry, right? If you want to adopt Kafka within our enterprises, then what can a typical architecture looks like? So that's what I'm going to present today, and we'll talk about the benefit of this architecture and how it can help us in the businesses, generate some revenues. So what you can see in the slide is the enterprise architecture, what can be designed, which is very generic. It can change as per the business and the industry where we want to deploy this. I'll start with the left-hand side, which talks about the streaming data sources. So if you look at the first box, right, which is the operational data sources. So what we are doing here is basically we are trying to extract the data and pull the data from this databases and then push into a Kafka. But then eventually you may have a question why we need to do that, right? And what is the exact use case where we will be typically doing this. So I'd like to just brief you about that. So today's industry, definitely they are revolving, and we are writing, the application which is adopting the next gen technology. But on the same time, we also have a legacy application which is running since over the years. Since we understand the Kafka and its capability, right? Everybody wants to adopt this within the application, but when we talk about the legacy application, everyone wants to be safe and secure. Nobody wants to make any changes, major changes within the application that can lead to instability, and that's what the bigger risk is. So, how do we ensure the capability like what Kafka is, or in fact any of the framework is giving to us? We need a way where we can adopt this within the legacy application, and that's where this operational database comes into the picture. So be it any application, whether it is legacy or in fact the traditional, at the end they will be writing the business data to the data sources, traditional RDBMS data sources, right? So at the end, I mean, what happens is, if we do not have any way within our application to write some code and extract those events, which is very useful for the businesses, we can go other way around. So once data comes to the database, RDBMS databases, right, we have a way where we can extract those changes, whatever happening within the database, either it could be an insert, update, or delete. We can extract those changes happening in the database and push into a Kafka. How we can do that? That's where the role of Debezium comes. So as you can see in the architecture diagram, Debezium is the tool that is from the Red Hat that listens to your RDBMS database, in fact, NoSQL as well, and pull the data that is, or pull the changes that is happening within the database and push into a Kafka topic. That's very useful tool. And Debezium as of now support some of the RDBMS and the NoSQL database like MongoDB. But the other vendors, the other database vendors are also coming from their option. So just for an example, Oracle got a separate tool which acts like a CDS. Use case, what Divya has presented in detail, that is around this only. So we have a Debezium that constantly look at the database, in fact, the database tables, what to configure, and then it tries to pull the information what it can, which is continuously changing and pushing into a Kafka topic. So that's the one line. So one way where you can extract the data, from the traditional sources and push into a Kafka. This is also called the event sourcing. You might have heard about this term. So that's how it works. Now let's look at what other sources we can have within our ecosystem, right? Where we are interested to pull those information. So other sources can include like our flat file, which is a TXT, XML, JSON, or anything tomorrow. So we might want to extract some of the information or critical information, which is very useful for the businesses. Server logs, that includes our Apache, in fact, the Docker. Let's say today the enterprise are heavily rely on the orchestration platform like Docker and the Kubernetes. You want to get the logs from them, try to understand overall health of the infra, what is happening on that side. IoT sensor, if industry is dealing within the IoT and they got a lot of sensors and the devices, you may want to pull out the information on the sensor values, what is happening. App activity in Clickstream is more about understanding the user journey, right? Whether it is on the mobile app or it is a web app, you want to understand how a user has, access the different pages, what kind of element they have clicked, what screens they have gone into it, and what activity overall they have performed. You want to extract all this information, which typically today it goes to a Google Analytics or other platform. In a similar way, what you can do is you can get those activities to a Kafka and then eventually, identify the user, and based on the user identification, you do some additional processing what is needed. And the other source of information could be a microservice, which is again a kind of a trending. And I think most of the organizations are working on converting their application to a microservices world, where you eventually have an opportunity to integrate with the Kafka. So we have a Kafka connector which can talk to a microservice, and from microservices you can export different types of events. So it can be a log event, it can be a business event, which is very helpful to understand what change is happening within the application. So just for an example, if somebody, did a shopping from the e-commerce application, you can say a product is sold or something, or other transaction is performed. So those kind of events basically you can extract from the microservices and push into a Kafka. So this is more about the data sources. Obviously, the source is not limited to this. Every business has a unique sources, and we want to extract the data from them. The other option is what you can do. You can write your own producer that can work closely with your sources, data sources, and extract the information and push into a Kafka. We can talk about that more in detail if needed. But yeah, as of now, this is, I would like to jump to the next part. Transformation. So once we have the data, right, in the Kafka, how we want to process them, that's what about more businesses working on. So we want to get maximum benefit of the data that we get and try to get the insightful that can be helpful to the businesses. It can be useful for the developer. It can be useful for the admin people who understand from the infra perspective what it is going on. So as far as the data processing is concerned, we have a couple of options today that we can adopt from the open source tool. So some of the options are listed here as a part of the streaming engine. So we have Apache Spark, Apache Flink, Samza, Storm, and the Kafka Stream as well. So this engine will give you enough capability to process your data, whether your data is in GB, or in fact, or in the bytes. But depending on the volume of your data, you can choose the platform which you want to use, right? That give you a capability where you can process the data, find out what you are interested in, and then push it to the other application. So with streaming engine, typically what we do is we have two ways. So either you can push the data to the other application which are expecting a more, what you can say, more fine-tuned data, I would say, or either you would like to store it to a data lake storage, which can be a typical NoSQL databases, or in fact the file system, or any other data source which a typical organization is using. So once we process the data, the fine-tuned data will get either stored into a database, or you want to push those data to a real-time application. That is the third part of the stream, right? So this data can be useful for the real-time application where some of the decision engine would be consuming it, and then it will be deriving some decision. You can use as an alerting that works more on the infra side and showing like, okay, what is happening. Fraud detection is again a different type of application that is written to understand if there are a series of transactions and to identify whether a particular transaction is a fraud or is the right one. So this typically data what is coming through the stream can be very well utilized by this application, and then they can generate some output that is very relevant to the businesses. On the other side, you can also ship data to an analytics tool, which is typically Amazon Redshift, or in fact the Elastic also. So Elastic mostly used to understand the log perspective, right? What is going within the application and trying to analyze the log. The third aspect of using this data is the data science. So some organizations, who are heavily relying on the machine learning and the data science capability, they would like to use this data to train their model, right? And once the model are trained, they will be deploying to the application to have the businesses serve. So this is more of an overall architecture, how Kafka can be placed, what are the different sources that we can work together, and then it can be easily processed through the different streaming engine that we have today. Now let's try to understand what kind of benefit that we can get from this architecture, right? Definitely this is a high-level architecture which is likely to change based on the industry for the customer, and there will be some minor changes into it. But overall, in general, as far as the benefits are concerned, these are the high-level benefits that you can get out of it. So first thing, it enables the processing of continuous data. So unlikely in ETL, what you have is the series of batch, right? And the data will be coming in the batch, you will be processing it, and again going or storing into the designated system. But here, with this architecture, you will be able to continuously process the data 24/7. There won't be any stop or any kind of pause that can force you to stop the processing over there. The other thing is the data scalability. So some industry works in a way where the data is not really fixed, right? So you might have a data coming from the sources in terms of KB. It can be MB, or eventually it can grow to GB. But with this architecture, what you achieve is the data scalability, and the streaming engine that we saw, right, that got the capability of processing such a high volume of data very efficiently. The other thing is the evaluation of the data source. So left-hand side, we saw in the previous architecture diagram that we had a couple of data sources. What happens tomorrow if something, we got a new data source that needs to be full, for the Kafka events? You can easily plug in the new data sources, which will not impact on your underlying existing architecture. Near to real-time processing, and that's one of the biggest benefits that we can get. Again, it depends on the organization what real-time means for them. Some might want to achieve the latency of the 100 seconds. Some may want to have, 10 millisecond, or in fact 1 millisecond, something like that. So based on the real-time requirement, what we have, we will be able to optimize, or in fact select the streaming engine that can enable us to get the data, desired business data, within the given time frame. Plus, if we have time series data, which is very sensitive, right? And I would say they are sort of the state management data. So one set of data is relying on the other set of data, and those kind of patterns we can easily identify using the streaming engine what we have. And the last benefit that we can get is the enable for compatible data architecture. So on the right side of the architecture diagram, what we saw, again, those applications can be changed anytime. You can keep adding the new application which is interested in your data, and then you can process them. So this is, in general, overall benefits that you can get from the architecture, real-time architecture, what we saw on the previous slide. All right, so I would like to hand over to Todd.
Divya, Rajesh, thank you very much. As some of you may have heard throughout the presentations here today, we've talked about Apache Kafka, and we've talked about Confluent. I imagine some of you are wondering, what's the difference? Tell me the similarities and differences between Confluent. Let's answer that now. So Confluent was started by the founders, the original creators of Apache Kafka in 2014. They developed the technology while at LinkedIn, trying to solve the challenges that we previously described. There's a very large ecosystem out there now today, as I'm sure all of you have heard of Apache Kafka. Over 60%, the last time we checked, over 60% of Fortune 100 companies are using Kafka in production today. Companies process actually over more than 1 million messages daily through Kafka, quite a bit more actually, so this slide's a little bit old. At the very essence of what Confluent believes, and has been alluded to in some of the previous slides, is that events are at the heart of every business. And a business is actually defined by the type of events that flow through their system, whether that's a sale or a trade or an invoice. The ability for a business to actually respond to these events in a way that's quicker and better than their competition is what's going to separate them from their competition. The Confluent platform starts with Apache Kafka, as shown here in black. Apache Kafka is made up of a few things that you heard today. It's Apache Kafka that itself, as well, a distributed commit log that enables the real-time processing of events. Then we've got tools around it, like Kafka Connect, which you heard Divya and Rajesh talk about as well. We've got Kafka Streams that allows processing of events in real time. And from there, the levels in blue is where the Confluent platform adds additional capabilities to Apache Kafka. So the platform itself distributes the very latest versions of Apache Kafka Connect and Kafka Streams, but we also add things in development and stream processing. There's too many to list here now, but my particular favorite is the schema registry. This is a tool you can use to ensure that the data that you're sending into Kafka adheres to a particular format, or as the name implies, a particular schema. At the top, we answer the question required by all enterprises. How can I secure this, and how can I operate this at scale? So Confluent also adds tools around answering both of these questions that are required to deploy to production in enterprises. At the bottom layer is another one of my personal favorites. The Confluent platform gives you freedom on how you wish to deploy. We know every organization is different. Some of you might feel like you have to deploy it on-prem in your data center or in a HIPAA-compliant public cloud, for example. Some of you might be interested in wondering whether or not the platform is available as a service. As you can probably guess, the answer to all of these questions is yes. And that's a differentiator for the Confluent platform, that you're able to have the freedom of deployment choice. Additionally, you're able to deploy in multiple ways and synchronize between multiple platforms, whether they're on-prem and in the cloud or on-prem and available as a service from Confluent. The bottom line is freedom.
Thank you. Thanks, Todd, Divya, and Rajesh. So before we take up the questions, I would like to briefly walk everyone through CIGNEX Datamatics. So talking about CIGNEX, we were founded in the year 2000 and are a subsidiary of the Datamatics group. We offer solutions and services on various open source cloud and automation technologies. Over the last 19 years, we've developed over 800 projects, and which have been seamlessly implemented by 500 plus consultants spread across the globe. Along with business, we believe in giving back to the community. Our team has authored 17 books on various open source topics and has made over 5,000 community contributions. Talking about our Confluent expertise, we are a Confluent partner and provide various services like consulting, architecture, design and implementation, integration, support and maintenance, and professional services on Confluent as well as Kafka. We have a certified team of Confluent experts who've carried out large-scale deployments. Along with this, we provide customized solutions on Confluent and Kafka. If you want to know more about our Kafka and Confluent capabilities, you may please visit our website, www.cignex.com. Now, we'll move to the questions. I have a couple of questions here. So the first one, which I can see here, is, can we leverage Confluence or Kafka's ETL capabilities if the data schema maps to the Avro objects? I think, Divya, would you like to answer this?
Yeah, I think Todd already covered this in pretty much details, that yes, Confluent and Kafka, basically it provides the capabilities, and Confluent provides the additional capabilities of schema registry, where it can map and utilize Avro objects if your underlying data system holds that.
Okay, I think this answers the question. I can see one more question here. It says, how to decide when to use Kafka Connect versus Producer to pull the data? So I think, Rajesh, would you like to take this?
All right. So this is really a good question. And one of the important thing is Kafka Connect, right? It's an API that gives you to write your own connector. So you can write varieties of the connectors that can pull the data from the different sources and in fact pulses the data into the end sources. If you go to the Confluent website, they've got a couple of connectors, right, from the community, and there is a whole repo for that. The other thing is, let's say if you're finding, I mean, the data source that you're looking for, the connector is not available. In that case, you will be writing your own producer or consumer that can pull the data right from the source, and in fact consumer that can process the data either to a topic or in fact the data source that you expected.
Hi, this is Todd, and I'd also like to add to that answer as well. As Rajesh mentioned, a key factor I would use to decide whether or not I was going to use the producer API or use an existing connector is by first seeing if a connector is available. The best way to do that is to go to confluent.io/hub. That's /HUB. And it provides what I like to think is a very easy, intuitive interface to search through hundreds of connectors that are already pre-built. And by connectors, we mean whether they connect to source systems or they write out to systems which we call sync. So that might be another way to answer that question, is to provide that resource to you on various hub connectors. And there also you'll find the connectors that are supported as part of a Confluent subscription and those that are totally open source and community based. So Rajesh, thank you. I just wanted to add to your very excellent answer as well with that reference for people as well.
Oh, yeah, thanks a lot, Todd.
Thanks, Rajesh. Thank you so much, Todd. I think we don't have any more questions here. So with this, as we have no more questions in the chat box, we would like to end the webinar. In case any of you have any other questions later on, you can write to us at info@cignex.com. We'll be glad to answer all your questions. Finally, I would like to thank all our presenters for today, Todd, Divya, and Rajesh. Thank you so much for presenting the webinar. And thank you everyone for taking time out to attend. Have a good day. Thank you so much.